Hello, all, and welcome to the organic chemistry lecture that continues our general chemistry lecture of the previous semester. So, in this semester, we will study organic chemistry. And first of all, let us define what organic chemistry means. So, across history, people or chemists were interested in studying the biological molecules found in nature. And they found that most of these, let's say, organic compounds, because they are natural, were made of carbon, or at least carbon was inside. So they were made of many other elements, but carbon was always present. And this is how they named this study field the organic chemistry, which means the chemistry that deals with carbon containing compounds. Of course, nowadays, yeah, we can also synthesize. So most of the carbon-containing molecules or polymers are synthesized and not just the ones available naturally. So, for example, if you take the graphite, which is what makes the pencil, um, it's also made of carbon allotropes, and you can see how these carbon atoms are structured um, in honeycomb shape. And for example, the diamond also is made of carbon network in a very structural way that you can see it like almost like a cube. And there are also carbon containing compounds that does not take part in the organic chemistry, which are the carbon dioxide, so the CO2, because it's mainly a gas, and so it is not considered part of the organic chemistry, and the reactions, the groups, and so on. And the carbonate, because it's an ionic compound, so it's the CO3 2 minus. Okay, so this is the carbonate. This is ionic compound that reacts with yeah, metals normally. So for example, we have the calcium carbonate or the magnesium carbonate. So you see, we have then a mineral composite, and here we're no longer talking about yeah, an organic compound. Um, because organic chemistry does not deal with ions. So this is just the inorganic chemistry part. Everything else containing carbon is part of the organic chemistry. For example, the biological molecules which I was talking about, you can, for example, see the hemoglobin, how it's made of carbon atoms everywhere, and these carbon are, of course, connected to other elements. Um, you know, the chlorophyll, which exists in the plants, and yeah, which facilitates the photosynthesis of the plants. So it's also an organic compound. And these are available in nature. So mainly the organic chemistry is focuses on these elements here in the periodic table. So carbon is always present. Yeah, hydrogen is more or less always present unless it's fully made of carbon, such as diamond, for example. You saw it's fully made of carbon atoms. And we can also have these other elements, so bonded to the carbon, replacing the hydrogen, for example, depending on the class of yeah, the organic compound, which we will of course learn. We will learn those classes, we will learn how to name them, so the nomenclature. We will learn the reaction schemes, so how they are formed and what other compounds they can form. The, the several reactions that occur until the end product is formed. So everything we will study in the organic chemistry module. And mainly we will focus on, of course, carbon, hydrogen, but also on oxygen and nitrogen mainly. And the others can also appear occasionally depending on the, yeah, like let's say the compound that we have. So for example, we will also study the chlorination of these compounds. So you will see we will deal with chlorine as well. Yeah, so the classes we distinguish the classes of the organic chemistry based on the functional groups. And functional groups means how the carbon atom is connected to which elements and how they are connected. So, for example, do we have a single bond or a double bond or a triple bond? And where are they situated? Are they end groups? So they are located at the end of the chain or in the middle of the chain. And this is what distinguish one class or one group from another. So before, of course, now we will talk about chemical bonds, but for this I need to take you back a little bit to the first semester, where we were talking about the atom in general. So the hydrogen atom, for example, you know that an atom contains a proton in the middle, in the nucleus, and the electrons are around. The hydrogen only has one electron, and therefore the hydrogen is composed of uh, one electron and one in one sphere. So this is the s sphere. This is the orbital where the electron has a probability to be in. So you can say as if it's a volume, but it's an imaginary volume. It does not exist. It's a function in space where that limits the probability of where to locate a specific electron. So the electron of the hydrogen can only be found anywhere within this sphere. And this is what we call an orbital. So this is the s orbital. Now, if we go further, for example, the helium has two electrons. And by the way, the electronic configuration is what distinguishes an element in the periodic table from another. So we cannot find any other element in the world other than helium that contains two electrons. So this is like the footprint of a specific element. Therefore, the helium here also, the two electrons of the helium are contained in the same s sphere or the first orbital. Now, the s sphere is saturated with two electrons. So, for example, helium has already saturated its orbital. When we go to this is the first level. So, we have the nucleus in the middle, and we have those orbitals around it. And we go from level 1 to level 2 to level 3 and so on. The more electrons we have inside the atom, then the more levels we need to occupy. The first level only contains the one sphere, the s sphere, and the s sphere normally can only contain two electrons maximum. And therefore, any element that has more than two electrons occupies already the second level. The second level, we also have the s sphere, which also can contain two more electrons, but we also have something else, which is the p orbital. So this is the s, and this is the p. The p has usually a bilobal shape. This is a p orbital. And here we can have an electron. And the p orbital has three-dimensional. So we can see it on three axes in space: the x-axis, the y-axis, and the z-axis. Sorry, I'm gonna draw this a bit better. Okay, and z-axis. So we call this, for example, py, pz, and here is px. This is three-dimensional. On each of the axes, we have a p orbital. They all belong to the p orbital. This is the px, this is the pz, this is the py. All this constitutes the p orbital. And in each of the lobe, we can have maximum 1 electron. So therefore, here the electron in red. If we have one here, and one here, and one here, we can also fill another one in the Z, another one in the Y, and another one in the X. So in total, we can have, in a p orbital, 6 electrons. Whereas in the sphere, we can only have 2 electrons. So now, let's continue. We were in the helium. If we add one more level, if you remember, we said that helium, we are already saturating the first level, because the first level is an exception and it only contains the s orbital. So it's already saturated with 2 electrons. When we have one more electron, we get the lithium element. That's the lithium, it's here. We have the lithium element, and for the lithium, we already are at level 2, because level 1 is saturated with 2 electrons. Then we are at level 2, and here we start with the sphere again. When we go to the beryllium, we have 2 more electrons, so these electrons are occupying the sphere in the second level. When we move further, we have the boron with 5 electrons. Now, with 5 electrons, we have the first level. The S sphere is already saturated. In the second level, here we have the sphere on the first level. In the second level, we have a sphere and we have the p orbital, if you remember, pz, py, px. So we have 1, 2, 3, 4, which are already occupying the S sphere, and we have one more. So this one can be in any lobe of the p orbital. This is for the boron. If we go to carbon, then we have 2 more. So 2 occupying the p. If we go to nitrogen, then we have 3. Oxygen, 3 in the p. So in total, we have 1, 2, 3, 4, 5, 6, 7. Oxygen has 8. You see, oxygen 8, so 8 electron. So this is the oxygen. So 3, 2 here, 2 there, and 4 here. So 4 electrons. These are a lone pair. So when we talk about the Lewis structure, here I will explain this in detail. So if you go to fluorine, for example, you have, for example, the X, one more, and then the neon, we have fully saturated orbital. So the P can contain maximum 6, and here we have 6. The S can contain maximum 2, we have already 2 occupying, and the first level is already occupied. So with a total of 10 electrons. So you see now, if we need one more electron, so we are at sodium, then we are at level 3 already, because level 2 is already occupied. So we start again with the sphere, we fill it, and then we go to the p, and so on. Now, in the third level, we start also having the d orbital. And then here, for the metal elements in the middle, we also have the f orbitals. But these are not part of our study program, so we will just focus on the s and p orbital for the moment. Now, what we talked about so far is based on the electronic configuration, which facilitates the the building of Lewis structure. So what is the electronic configuration? It's what you see here. So all the elements belonging to this group, for example, have the same electronic configuration, and it determines the number of electrons in each of the orbitals and each of the levels. For example, if we say boron, boron belongs to the second period, which means the electrons extend over two levels, and the first level is saturated, of course, because we only have s orbital, which can contain two electrons, so the s2. And in the second level, we have another s2, and we have the p orbital, which contains only one electron, because the more we go from left to right, we have to add one electrons to the peripheric orbital. So here we have one electron, two electron, already two electrons saturating the s sphere of the second level, and then we have one electron in the p orbital. So therefore, px only is occupied and with one electron. This indicates how many electrons are occupying the specific orbital, whether s or p, or px, py, for example, pz, and so on. So for example, if we take the oxygen belongs to the second level, so second period, which means it has two levels of orbitals. So what we care about is always the this level, for example, the upper level, because it's the one where the electrons can move. The other ones are very much connected close to the nucleus, and you know the charge in the nucleus is positive and the electron has negative charge. So these are very well connected together. Therefore, the only electrons participating in chemical reaction are those belonging to the um, yeah, peripheric level of orbitals. So we only talk about the upper one. So if it belongs to the second period, we only care about the second level of orbitals, because this is the one that reacts. If it belongs, for example, the fourth period, then we only consider the fourth level of orbitals. So let's go back and talk about, for example, oxygen. So oxygen, if you see, it belongs to the second level, which means the electronic configuration should end with 2, because it's the second level, S2, P3. P, when you write the electronic configuration, you sum up all the Px, Py, and Pz together and only write P, so P3. This is how the electronic configuration should end. Of course, we also have in the first level 1, which means the first level, S2. We have only the S sphere in the first level, and it's saturated with 2 electrons. So in total, we have 2 plus, sorry, we are talking about oxygen, so it's not 3, it's 2 plus 1, it's 4. So B4. Okay, so this is the full electronic configuration of oxygen. You see, in total we have 6 electron and 8 electrons. So 2 plus 2 is 4, plus 4 is 8. In total we have 8 electrons, and it's indicated here. So this is how we write the electronic configuration of a specific element. Now we only care about this one, the upper level, which is the second, in the case of oxygen. When we need to write the Lewis structure, we only care about the level where the electrons are most probably to react with other elements. You see here, this is the oxygen. You have 2 electrons in the S, let's say this one, and you have 4 electrons in the P. Why do we have here? So the S is already saturated, that's why we have a lone pair. This line means we have 1 electron and 1 electron, and they are already saturated, so they don't, most probably they don't react with other elements. So these do not make a bond with another element, whereas these are free electrons and they can bond with another element, for example, hydrogen. But let's explain exactly how this is, why this is written, why do we have a lone pair here. So let's take the example of oxygen again. Oxygen, in the second level, we have the S sphere, which already has 2 electrons. Remember, in the first level, we have the S sphere, so 2 electrons are already considered. Now in the second level, we have 6 electrons in total. And if you know what the octet rule means, it means in one level we can have maximum 8 electrons. So for example, if you take the example of a neon, in the second level you will have 8 electrons, 2 in the s sphere and 6 in the p orbital, because you know that we said the p is saturated with 6, 2 in px, 2 in py, and 2 in pz. So the total in one level is 8, and this is the octet rule. So which means it's saturated, and if we need to add 1 electron, for example, to get the sodium, then we need to start a new level of orbitals, which is the third. Now let's go back. We have 6 electron in the second level. This is the s, and we have the p. We have px, so this is pz, let's say, py, and px. These are orbitals. Okay? And in each of them, in each of the lobes, we can only have 1 electron. So the electron can be either here or there. So let's say it's here. First, the electrons fill the different axes, and then if we have more electrons, we start filling the rest. So we don't start filling, for example, 2 in pz and leave the px and py empty. We start filling 1 in each of the axes, and then the remaining 1 fill the second lobe. When we have 2 in pz, for example, it's fully occupied, this is what we represent with a lone pair in the Lewis structure. So when you see this, it means this is already saturated. So it's either coming from the S sphere, because it can be saturated with 2, or coming with Px or Py or Pz, which are both saturated, which means they cannot receive, they don't have a capacity to receive 1 electron from another donor, let's say, or from another, they cannot bond with another atom. I will explain this. So now let's go back to the oxygen. We have 6 on this level. 2 are already filling the S sphere. This is the first level. This is the second level. So this is the first, this is the second. In the second, we have the S and we have the P. Yeah, this is the Py, this is the Pz, and this is the Px. So we start filling 1. We have 6 in total, right? So 2 in the S, and now we need to add 4 more. So 1 in Pz, 1 in Px, 1 in Py, and the second one can be in either of Px or Pz or Py. Let's say in Pz. So how to draw the Lewis structure then? This is oxygen. It has 2 electrons from the S, which is a lone pair. Yeah. It has 2 electrons from Pz, which is also a lone pair. And it has 1 electron in Px, 1 free electron, and 1 free electron from Py, which means the oxygen can still receive 2 electrons, 1 in Px and 1 in Py. And when it receives, for example, 1 electron from H, we get a bond. And here we receive another electron from H, Py, we get another bond. How does this actually work? So we don't have a line, this is just imaginary, this is just a representation to visualize how the elements are connected together. But in fact, there is no such thing that an electron is connected to another electron with a line. How does it work? Again, the oxygen, these are the orbitals that can still receive 2 more electrons. We have 2H, and the H only has 1 electron, right? So the electron is residing inside the S sphere of the first level. This is I will draw it in another color. Let's say green. So this is 1H having 1 electron, and this is another H. How do they share their electrons together? Why is it a covalent bond? So when it's an ionic bond, it means the H is completely losing its electron and giving it to the oxygen. And in this case, we get H plus, which means that the H has lost its electron and now it has an empty sphere with only the nucleus with a positive charge in the middle and no electron. And that's why it is one time plus. So it's an H plus in the case of an ion here. Um, Same for when we have a negative charge. It's when an anion receives an electron on top of what it should normally have, and therefore it will have more electrons than the protons in the nucleus, so it will become negatively charged. This is another case here. Now we are talking not about ions, we are talking about covalent bonds. So the electrons are sharing and not being donated. So the electron still remains to H, but at the same time it belongs to oxygen, or it's shared with oxygen. How is this possible? The H comes closer to the oxygen and bonds here. The electron that was already residing in the s sphere of the hydrogen. So this is the space where we can find now this electron, which is the space shared by both the s sphere of the hydrogen and the p orbital of the oxygen. And when this electron is always present here in this space, it contributes to the electronic configuration of both the hydrogen and the oxygen. So now in this case, both elements have saturated their octet rule. For the case of hydrogen, there is no octet rule because it is saturated already with 2 electrons because it only has one level, and in the first level we only have a sphere which can receive 2 electrons maximum. So now when the H is bonding to this px, all the space, because this is one orbital, so all the space here, px plus the hydrogen, is becoming like one molecular orbital, we call it, because now it's a molecule. And therefore, the hydrogen now has 2 electrons, one here and one there in this molecular orbital. And the px also has 2 electrons. So the px has gained 1 electron, and the oxygen now has 7 electrons in total instead of 6. So it gained 1 electron without taking this electron from H. And that's why here there is a covalent bond and not an ionic bond, because H did not give up its electron. If this H comes also closer to the Py, we now have another electron here, which was originally belonging to H. Now it's belonging to both H and Py. So this is the space now, the new space, Py and H. Now we have 2 electrons in this, and it's saturated. So in total, that's why we have H2O. When we have the H2O bond, this is oxygen, this is hydrogen, and the lone pairs are the electrons that already belong to the oxygen in pz, remember, and in the s sphere. This is coming from s, and this is coming from pz, because they are already having 2 electrons and they cannot bond with so the H cannot come, for example, to the pz because it's already saturated here. So it cannot receive one more electron. In exceptional cases, it can, but in the case of HO2, it doesn't. Now, if we need to consider the case of an organic compound, so for example, methane, which is the smallest organic compound, which is a compound that contains carbon atom, and a carbon atom, according to the Lewis structure, carbon is here, it can bond to 4 different electrons because carbon has 6 electrons in total. So again, if we go to the whiteboard, we have the first level. The first level has 2 electrons, the second level has 2 electrons in the sphere, and we have the P. So this one. We have 6 in total, 4 are already drawn, and we have 1 and 2. So normally we should write the Lewis structure like this. 2 from S sphere, 1 from Py or Px, 1 from Py. So carbon normally can only bond with 2 more and not with 4. So how is that possible? How is carbon bonding with 4? So the methane is CH4, and you saw in the periodic table that the Lewis structure of carbon is written like this. How is this possible? If you consider, for example, the H bonding with a p orbital, let's say, one H can come here with 1 electron, another H can come here with 1 electron, and a third H can come here. And what happened to the fourth? How is it possible to bond? Because we no longer have p orbitals, so the H can only this is one. This you will say, okay, what about this? Maybe H can come here, but this is actually one orbital, so it's 2 lobes, but it's still one orbital. So this one is one orbital. And the H in general, when it bonds to the orbital, the molecular orbital will become like this. So the full space will become together. So another H cannot come here. And how is this possible that the carbon can bond with 4 hydrogens? It's because of something called hybridization, which occurs in organic chemistry. So with the carbon in general, or in particular. And when we have the s sphere and the p orbital forming one sp orbital, so we no longer have s alone and p alone. Now we have sp together. So in the case of methane, we originally had one s and 3 px, bz, py, if you remember. Now, when we have C and H, new orbitals are formed, and they are called sp orbitals. So because we have one s and 3 p, the new orbitals will be sp3 because it's made with 3 p orbitals and one s, so sp3. And we have 4 of them because the new orbitals will be, so we no longer have 1s plus 3p, we have 4 equal sp3. So instead of having s sphere alone and having p orbital alone for the carbon, now the carbon has 4 sp3 hybrid orbitals, which are equal. And this is how you can visualize it. We start from S and P, but for the case of carbon, for the case of methane, not carbon alone, because carbon can be part of inorganic chemistry, when it connects with hydrogen, now the hydrogen is no longer bonding to the P of the carbon because it cannot bond to the S, of course, because S is already saturated. The hydrogen can bond to 4 different sp3 orbitals, which are equal now. Because S and P were not equal, they had different shapes, different energies, and so on. Now, the sp3 hybrid orbitals are equal, and each of them holds one electron for the carbon, coming from the carbon, and in the other lobe, they can also receive one electron coming from hydrogen, for example. So we will get one electron here, one here, one here, one there, coming from the shared electron of hydrogen. And therefore, this carbon can bond to four different hydrogen atoms. And we get the methane. And the methane has a tetrahedral structure because of these sp3 hybrid orbitals, which are equal. And therefore, the carbon will be in the center of the molecule, and the hydrogen will be from equal distance of the carbon. The tetrahedron has this shape. So you see four corners where you can imagine the H resides. So we have one H here, one H there, one H here, and one H there. And the carbon is just in the center of this tetrahedron because it should be from equal distance, at equal distance from all the four hydrogen. Because of this, these equal sp3 hybrid orbitals. So this is the concept of hybridization. Now, in the case of methane, we only have single bonds, yeah, because the S, when we have one S hybridizing with three p orbitals, we get four different single bonds because this is the maximum. Yeah, four is the maximum bonds that carbon can make, of course, because it has only four electrons. When we have one S bonding or making hybridizing with only two of the three p orbitals, in this case, we start having a double bond. For example, in the case of C2H4, ethene. In the case of ethene, we have two carbons. So this is one carbon and this is one carbon. And I will draw to explain. So what happens in the case of ethene? We have two carbons, one here, one there. Every carbon originally has one s and three p orbitals, right? Same for this. One s, this is the s, this is the p. S and three p orbitals. Now, as explained with the methane, the s and p hybridize together, but not all the p orbitals, only two of them. So if you see here, only two of the p orbitals hybridize with the s and form three different sp2 orbitals. It's called sp2 because it's only made by two p orbitals. So we get, instead of one s plus two p, we get three sp2. And the third p, which is, let's say, pz, remains unchanged. So here, this px over here, we had it originally like this, separate. Now it hybridizes with the s and forms a new sp2 orbital. So the px will become this. And the py also was a full py. Now it hybridizes with s and forms another sp2. We have another sp orbital, as we said. So you can see here, now we have three sp2 orbitals, as said. And this one, the pz is unchanged. This pz is unchanged. It originally had one electron, and here it had one electron. And now each of this sp, so if I want to draw it again, what we have here will become the y, the x became one sp2, right? The y also became an sp2. The pz remained unchanged, so it's still pz. This one is pz. This one is sp2. We have sp2 and another sp2, and the pz is still pz. But we said originally we had one s and two p from each of the carbon. Now we have three sp2. So the third sp2 will also be here. So now we need a third sp2. Okay, around of each carbon. So this was originally the s sphere plus two p orbitals. Now we have three sp2 orbitals. You see here, one s sphere is hybridizing with only two p orbitals, and the third p orbital is remaining unchanged. So in the carbon originally we had four electrons, one in each of the sp2 and one in the pz, right? Same here, we had one carbon in each of the sp2. There is another sp2, of course, because they are three in total to make it up for one s plus 2p. So this one had one electron, and the pz also have one electron. Okay, so now it's easy to make those bonds. We have two hydrogen bonding with each of the carbons. One of the hydrogen will bond to this sp2, let's say, here. And the other hydrogen will bond to this sp2. Okay, so these are already saturated, this one and this one. We still have possibility for the pz, and this one, this sp2, has still a possibility to make a bond. So same here, the one hydrogen approaches this, and the other hydrogen approaches this. So now we have this saturated. Okay, I'm gonna mark it as saturated. And this one is also saturated, if you are following me. So this orbital here, all of it with the H, is saturated until here. Okay, now we have possibility to receive one electron here in the pz and one electron in the sp2 orbital. And same here. So this is saturated already. And with the H's also, this one is saturated. So we still have possibility to receive one electron here with this orbital for the pz and one electron. So what happens? We already have 1H, 2H, 3H, 4H. These are H's. H, 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 and H. And the element that we are talking about is C2H4. This is the ethene. So each of the carbon receives two hydrogen, which is already completed. Now the rest, in order for the carbon to complete its octet rule, because it gained, each carbon had originally 4 electrons and now received 2 more hydrogen with 2 more electrons, so it has 6 electrons. How will it get its 8 electrons? So because it still has capacity to occupy 2 electrons here, one in the pz, one in the sp2. In this case, the 2 carbon will bond together and share their electron with each other. So this sp2 orbital will bond with this and will share their electrons, so they will come closer, of course, and we will have a molecular orbital of all this. Of course, they will be closer to each other. So this is originally was the s sphere. It originally was S sphere and now it became the sp2. And this one was originally pz and it's still pz. So this is pz, and pz will also come closer and will make a bond. So when they make a bond, the whole, this and this and this and this will become one bond, one full bond. It's not two bonds, it's just two lobes, but it actually has in total one electron here and one electron there. So if you see it here, this one, which was originally PZ, and here PZ, is now one full bond. So this is one bond. One electron was here, one electron was there, and now they are sharing. So this one has two electrons, and this one has two electrons. So they are making one bond together from up and down because they have two lobes, but it's actually one bond because the full orbital, the pz orbital as a whole, as one orbital, is just creating one bond with the other pz orbital of the other carbon. When the new bond is coming from a p, from an original p orbital and not a hybrid sp orbital, then it's called pi bond because it's originally coming from p and p. You see pz and pz. When it's coming from sp orbital, so a hybrid, then it is sigma bond. This is an sp with an s. So here we are only talking about the carbon orbitals, and the hydrogen orbitals are still the s sphere. So the bond actually is taking place between the s of the hydrogen and the sp of the carbon. The bond here, the sigma bond, is sigma s sp because it's between the s sphere and the sp hybrid orbital of the carbon. Whereas between the carbon themselves, so between this carbon and this carbon, the sigma bond is sigma sp sp because both are now hybrid orbitals coming from carbons. For the pi bond, it's pi p p. It's always between two p orbitals and not between hybridized orbitals. So when we have a pi bond, here we have a double bond. The double bond, so if we want to draw the structure of the ethene, we have one H, as you see here, and between each other we have the sigma bond, which is the sp, sp2 and sp2, plus we have the pi bond, which is coming from the pz of each of the carbon. So this is what makes the double bond. When we have one pi bond plus one sigma bond, in total we have a double bond. And this takes place when one of the p orbitals does not, one or more, does not participate in the hybridization of the s and p orbitals. So the same thing if we want to consider, for example, ethane with two carbon atoms only bonding with two hydrogen atoms. So each one is only receiving one hydrogen. The rest of bonds, the rest of electron sharing is taking place between the carbon themselves. How does this happen? Instead of having one p orbital that is unchanged, now we have two orbitals that are unchanged. So originally, in each of the carbon, we had two electrons in the s sphere and one occupying each of the p orbital. This is, for example, px, this is py, and this is pz. Pz was empty. So pz and py are still pz and py, did not contribute to the hybridization. And now only one of the p orbitals, which is px, plus the s, are giving us two different equal sp orbitals. This is called sp because only one of the p is contributing to the hybridization and the rest are unchanged. So in this case, 1s plus 1p, we get 2 sp hybrid orbitals. And these actually are the ones that will receive the H sphere. And the rest will be unchanged and will just put their electrons together to saturate the octet rule, and we get pi bond with py and a pi bond with pz. We will get a triple bond, one coming from the sigma bond, which is sp of each of the carbons, and the other two are coming from the pp bonds. So we have first carbon, second carbon. We said that the one sphere is hybridizing with 1p. So this plus this will give us 1 sp, 2 sp, because we originally had two different orbitals. Now we have, instead of one sphere and one p orbital, we have two sp orbitals. And the rest will just stay as normal py and normal pz. Okay, for each of the carbon, this is happening. So what do we get? 1 sp and another sp and 1 py and 1 pz. So 4 different orbitals. Each of them have 1 electron. This one has 1 electron, this one has 1 electron, 1 and 1. Now, the H will approach this, the sp, of course. The H will bond with the sp, and we will have here 1 electron. So this will be fully occupied already. This sp, this one of the sp will be fully occupied. And the same here. 1 pz full, py is full. The s sphere became sp, and the px became also sp. So 1h will approach this. Also, we have 1 electron originally in each of the carbon orbitals. So 1h is sharing the electrons. So we have this orbital now saturated. What happens for the rest? It only gained 1 electron. So the carbon has originally 4 electrons, and it only gained 1 electron, 1 more electron from the H. What about the 3 more to get the 8 electron in total? They put them together because they have capacity still in the 3 of orbitals to receive 3 more electrons. They put them together, they share them together, 1 coming from the sp orbital and 2 coming from p orbitals. So in this case, this sp orbital, these two sp orbitals are bonding together to saturate themselves. So we have a sigma bond because it's coming from sp bonds, right? sp, sp. And here, in this case, we have one sp sigma bond also, sp and s, because the H is an S and the sp coming from the carbon, the hybridized sp. So here that we have single bonds. So this is the first C, this is the second C, this is the H, and here we have a single bond with H because it's coming from sigma sp s. Same here. Also, between the C themselves, the sp and the sp are bonding together. We have a single bond called sigma sp. So this is sigma. This is the single bond. Now the rest, originally being pz and py, or px, let's say. This is pz, this is px, are bonding together. We have this bond, pz and pz. This is one bond. They are putting their electrons together. Now we have, instead of one electron in each pz, we have two electrons in the full pz-pz bond. And same for the px, they are also bonding together. So in this case, we have one bond from pz, another bond from px, and the original sigma bond from sp orbitals. So we have a triple bond here, 1 and 2. So this is how we draw the structure of ethine, which has a triple bond. Here we have a C, here we have a C. Each is bonded to one hydrogen, and the rest is a triple bond between them. One is coming from sigma bond and two are coming from the pi bond. Now what's characteristic about this pi bond? If you see it, it's connected from above and below, and it's as if you have a ring on top from each side of the molecular axis. This is the axis of the molecule, and here we have kind of the electrons are residing like a ring on top, and here also, and we cannot break them. So if we rotate the molecule, this bond will break. If we didn't have this pi bond, if we only had the sigma bond, if we rotate the molecule around this axis, nothing will happen. If we rotate this, for example, like that, and the other from the other way, so like kind of twisting, the molecule will stay the same. Nothing will happen. However, if we have this pi bond, the molecule will break if we rotate them. And this is a special characteristic about the pi bond. So carbon usually connects via 4 single bonds, or 2 single and 1 double bond, or 1 single and 1 triple bond, like in the case of ethine, for example. 1 single, which is with the hydrogen, and 1 triple bond with the other carbon. And another characteristic is that the sp3 has a tetrahedral shape. We talked about it, like in the case of methane, tetrahedron, because it's composed of 4 equal sp3 hybrid orbitals, or trigonal planar in the case when we have a double bond, or linear when we have a triple bond. And only atoms connected by single bond can rotate against each other, like in the case of, for example, here we have a single bond between carbon and carbon. But when we have a double bond between them, then it's not possible to rotate the molecule without breaking the whole molecule. So we get completely different products. So that was it. And in the next video, we will see a bit of repetition about also part of the first semester, which is electronegativity, and to understand the attractions between the different elements.